floor stage is yours.
Yeah, thanks a lot, Nathan. And so thanks a lot for the invitation to speak here. So it's really a pleasure to present some of our latest results here. Yeah, exactly. As Nathan said, I want to talk about high energy physics at ultra cold temperatures. So usually when we think about high energy physics, then there come into mind pictures like this here of the Alice detector at CERN, for example, where experimentalists smash heavy ions into each other, and then out of this heavy impact, fly lots of particles out, and from their trajectories, they try to reconstruct what happened actually during the collision event. No, you can imagine that this is a very daunting task, but it's not only a huge effort for experimentalists, it's also a huge effort for theorists to try to compute what is the dynamics of quarks and gluons during this impact. Yeah, so in fact, computing these type of questions and other questions from nuclear and subatomic high energy physics is one of the main drivers of high performance computing, of scientific high performance computing. And so what we want to do is we want to bring in a third player into the game, so to say, namely the quantum simulator. And this can be indeed cold atoms and optical lattices, which I'm going to talk about today, but there are also much efforts in trapped ion or superconducting qubit devices, or also photonic devices. And so just as a, to clarify, the quantum computer is certainly not going to replace any of the other two players. It's more thought as a complementary tool. So there are regimes where classical computations are very, very good, especially in equilibrium, and one can do quantum Monte Carlo calculations, for example. And of course, then we want to use the classical computers. But other situations, oops, sorry. I got some technical issue here. Okay, sorry. WhatsApp tried to hijack the computer. Okay, sorry. Yeah, so there are other situations like when the system is far from equilibrium, where classical computations are very hard, and there maybe we can get new insights using quantum computers. But of course, also one should also state that the experiment is never going to be supplanted, because the experiment is the final arbiter of what nature does. So what we compute here, we derive models that we think describe nature, and then we try to solve these models and see what physics do these models contain. And then we can compare to experimental data, but we can only get what we put into the model, so to say. And but that's already very interesting, because usually it's hard to solve these models, and then we cannot even compare to the experiment because we don't have the solution of the model. Yeah? Okay, so yeah, so we want to do something that is relevant for high energy physics, at least in the long term. But if we want to solve that question here, this would require quantum chromodynamics in 4 space-time dimensions. So that's very, very challenging. So we're going to go a step slower and do models that are simpler, but which still contain interesting physics. So that's one of the tasks that we have to do. Identify models that can be realized, which still reproduce some of the physics, even if they cannot quantitatively explain what happens in the experiment. Okay? So still to get some insights, what can happen in lattice gauge theories and so on. Okay? Okay, so here's the outline of my talk. First, I'm going to show you what is the model that we are working on here mostly currently. Even I think in the community, this is the most chosen benchmark model. Then I'm going to show you that there are relevant phenomena in this model, even though it's simpler. Then I'm going to discuss some scalable implementations using cold atoms, and also discuss some work that we are doing on trying to make sure that these systems work reliably. And then, okay, in the end, I will conclude. Yeah, so let's start with the benchmark model. So as I said, so we want to do high energy physics. So, the framework that we should look at is the standard model of particle physics. And there the interactions between different particles are governed by gauge theories. So for example, for these heavy ion collisions, we have here gluons and quarks that interplay. And that is governed by quantum chromodynamics. That's an SU3 gauge theory, which is very complicated. So maybe let's look for something simpler at the state where we are right now with these devices that we have available. And well, here, for example, we have the electrons and the photon, and these are governed by quantum electrodynamics. So that's a U1 gauge theory. It's a much simpler symmetry, needs less degrees of freedom. So that's very nice. So maybe let's take this one. And yeah, so we'll go even one step simpler. We take it just in one spatial dimension. So then this, and as you're going to see, there's still lots of interesting physics in this model. Yeah, but just because we want to implement this, I think it's useful if I walk you through the Hamiltonian. Okay, so what do we have here? Here we have fermionic spinos, which describe electrons and positrons. And then, for example, this term here counts how many we have. So this gives just the rest mass of electrons and positrons. But now these should be dynamical particles. So they should be able to move. We have a kinetic energy. There's just one derivative because we are working in a relativistic theory. And then, but now these should be charged particles. So this means there has to be a field line between the positive and the negative charge. And now even more, well, so first of all, this electric field now has also an energy. But even more, if this electron moves, then the field should not just stand around there, but it should adapt immediately to the new configuration. And so to do this, so that this interplay, the kinetic energy of the fermions is coupled to the electric field, we add here the vector potential in minimal coupling. Okay, good. So this is our target model. We want to have these coupled degrees of freedom, and they give us interesting physics. But now the crucial thing is it's not sufficient just to have different degrees of freedom. So we, I don't know, we take a cold atom system and we throw fermionic and bosonic atoms in there. Maybe they generate some interesting many-body effects, but here we want one specific model, namely quantum electrodynamics. And so that's one thing that we have to fulfill, namely the defining quantity of a quality of a gauge theory, which is the local gauge symmetry. And here, this is nothing else than Gauss's law, which states that the divergence of electric field minus the charge density has to be zero. So if I write the generator of the symmetry here and apply it on the state at any position and any time, then this should always be zero, and G should commute with the Hamiltonian. So this should give us zero. So then it's a conserved quantity, really. Okay, so it's a symmetry, it's conserved and local in the sense that it applies for every position. Okay, so now pictorially, what this means is simply that a positive charge is a source of field lines, a negative charge is a sink of field lines, and then we cannot have situations like this where a field line stops somewhere in the vacuum. So this is not allowed. Yeah? And that's now the art of generating the dynamics, that only certain configurations are visited by the quantum simulator and others not. No? And the difference is in nature, we postulate that the Hamiltonian commutes with Gauss's law and only these configurations are seen. Here in the quantum simulator, we have to do something for it. And that's the big challenge. And this is also why it's more challenging, maybe these type of quantum simulations than just the Bose-Hubbard model, for example. Okay, so before we come to the implementation, just briefly, so now we have this model which we took a simple gauge theory and only in one spatial dimension. So we can ask, is there actually interesting physics to be found here? And the answer is yes. So for example, there's a quantum phase transition in this model. It has to do with some topological properties of the vacuum. So okay, don't need to care too much about it. For us, we can just understand this as having a background electric field of half a quantum. Okay, so then this would be our system. There's half a quantum of electric field that comes in and it comes out again. And now we can ask, what state does this system take? And well, if the mass is very, very small, then this means that we want to have lots of particles. So what's going to happen is that there are electrons and positrons which will pop out, and then they will overscreen this incoming field. So the field comes in, it's overscreened, so there's half a quantum going in the opposite direction, it's overscreened again in the opposite direction, and so on. And so if you look at the average here over the system, there's actually no electric field in there. Okay, but now we can see what happens if we increase the rest mass. Well, at some point, it's not favorable anymore to have different charges in there, so they want to annihilate each other, the electron and the positron and so on. And so what we will get is just an empty system. And now this electric field can just pass through the system unhindered. Okay, but this is not the only situation that can happen. It's actually this electron here could also annihilate with this positron here. And then we get, and so if we go through this entire system like this, then we get a situation that looks like that, where we have a positron here and an electron here on the boundaries. So they overcompensate the field, and now it passes through the system in an opposite direction. And so this is just a little boundary effect, which in the thermodynamic limit doesn't play a role. And so these two situations become completely degenerate. Yeah? And so this means if we increase the rest mass, at some point we will have a spontaneous symmetry breaking if we collapse into this configuration or that one. And so there's a critical point in between. Yeah, this is actually known since the times of Coleman many decades ago. But more recently, for the specific model that we're going to look at a little bit later, has been calculated in this work here using tensor networks. And indeed, they see that if you look at the electric field as a function of the rest mass, then there's essentially a region where it's zero, which is this screen situation, and then it comes up and it goes to a large value, which is when it takes one of these two domains. Okay, so let's say now this is our target model, and let's say this is our target physics that we want to see to benchmark if we can actually see interesting many-body effects in such quantum simulators. And so the question is how to implement such a thing. Well, just to briefly give you an idea in the community, I think there are two main approaches to realize gauge theories in the quantum simulation. One is actually to use Gauss law. We know that this is a conserved quantity. So we use that to throw away all configurations that are not allowed. And then the system only fulfills these. And this is usually easier to do in a universal quantum computer, where we just decrease the unitary that we want and then implement that unitary. And so there's many works, especially in trapped ion quantum computers, superconducting qubits, and also in a Rydberg atom. Now we can call it quantum computer or quantum simulator, depending on your taste. Yeah, but in these cases where you have lots of possibilities to tune the unitary, especially, for example, in the trapped ions and superconducting qubits. But there's the second approach, where instead we keep both degrees of freedom, the electric field and the matter field, and we don't remove these additional configurations a priori, but then we need to make sure that dynamically the system remains only in the good subspace. And for this, one can use certain symmetries or energy penalties or combinations. And this is usually what some things like this is done in the cold atom context. So I also should point out Monika Eidelsberger, who you know well in Munich, she's realized a Z2 gauge theory using a Floquet approach, which I guess one can also see as an energy penalty, as a fast rotating thing that suppresses undesired transitions. Okay, so there are these two approaches, and just to give a taste of their advantages and disadvantages, I think actually both are very interesting. This one of integrating out, it uses very efficiently the degrees of freedom that one has, because it doesn't put additional degrees of freedom to then restrict the configurations that one allows. And it has in the last years been very much developed into a general framework. Now people know how to do this for non-abelian theories, for higher dimensional ones, and to do it in a way that the resulting theory is still local and so on. But still, nevertheless, the resulting interactions can be quite complicated. So it's still a challenging thing to implement. And there's also this problem that sometimes an error doesn't have a very natural interpretation. So if I've integrated out, so this integrating out, what it means, essentially, maybe to clarify this, I can use Gauss's law, for example, to replace the electric field everywhere in my Hamiltonian by as a function of the fermions of the matter fields, because I know from the matter what the electric field needs to do. And then I simulate only the matter fields. But now it's a sort of addressed matter field that drags the electric field around. And so if a local error happens, that a fermion pops out, then it's I interpret this back as something happens to an electron plus the electric field, and now it becomes a very complicated type of error term, or can become a complicated one. On the other side, when you keep both degrees of freedom, it has also advantages and disadvantages. So the one thing that I find is nice here, that then you can, so here you have used Gauss's law, you have removed all undesired configurations. So then that's it. You have, again, as a sort of a postulate, put it into the system. If you keep both degrees of freedom, then we can actually test what violations of Gauss's law do. Can gauge invariants emerge in nature, even if it's not a postulate that comes beforehand from nature, but as an emergent quantity. These types of things that we can test here. Okay, but we need to ensure that the gauge symmetry is kept by some other means, which can also become complicated. Yeah, so I think both of these approaches have their justification and should be pursued. And what's also interesting, both are reaching now dozens of qubits. So it's now becoming really hard for tensor network methods to compute if they do far from equilibrium dynamics to keep up with them. I think right now they can still do it, but it's now becoming, it's not just something very, very immediate. You have to try a little bit to do the tensor network calculations. Good. So here, just to focus on one thing, I'm going to discuss only two experiments where we were involved, where in this context of keeping both degrees of freedom in the context of cold atoms. And so here, our workhorse, so to say, is the Bose-Hubbard model. Just as a reminder, we have a periodic lattice potential, and then we have bosonic atoms, for example, in there, which can tunnel between lattice wells. So we have a kinetic energy, and if they meet, they interact. So we have also an interaction energy. And so these are the basic building blocks. There are many, many extensions which we are also going to use. So for example, one can also put fermionic atoms in the lattice, or you can use mixtures, you can use different internal states, super lattices that have different chemical potentials and so on. So there are many, many possibilities to play around, and but in the end, somehow it boils down to chemical potential, kinetic energy, or interaction. Okay, good. Now we want to use this to realize QED. Now I showed you before QED in a continuum. So here we're now talking about optical lattices. There's one reason we want optical lattices, because we have all these knobs to tune around. So there's really a toolbox to use. But there's also a conceptual reason. Namely, we want to study here a relativistic theory. Okay, so we have this one derivative here, which is given by a Dirac cone in the dispersion relation. Now, atoms are non-relativistic particles. They're very heavy, so they have a parabolic dispersion relation. And so if you want to simulate something relativistic, one way to do this is by putting the atoms into a lattice, and then we can do band structure shaping. And in the band structure, we can get Dirac cones and then work around these Dirac cones. Yeah, so that's why we also want, really conceptually, want optical lattices. And so now there are many ways to discretize actually this lattice, this continuum Hamiltonian, which have advantages and disadvantages. Here we use one, which is the so-called Kogut-Susskind formulation. So that one just takes the spin or the electrons and positrons and puts them on alternating lattice sites. Okay. So now we have two atomic bases, and then we look at if one looks at the band structure, one sees that there's a Dirac cone, so that's fine. So the fermions sit on alternating sides, and then in between we have the electric field on the gauge links. So now the discretized version of our Hamiltonian becomes this. Electric field is just discretized. The fermion rest mass, as I said, we split electrons and positrons on alternating sides. So we interpret one of them as electron and positron, and so they get alternating rest mass. And then the kinetic energy is just a tunneling of the fermions. And now the minimal coupling appears up here. So that's nothing else as if the fermion tunnels and moves along the link, so here, from here to here, for example, then it picks up an Aharonov-Bohm phase that corresponds to the gauge field sitting on the link, and this appears here. Only that it's not an external magnetic field or so, but it's some dynamical quantity and there's some feedback. Okay, so this is our discretized Hamiltonian that we want, and then we have in addition a discretized electric field, which enters the Gauss's law. Yeah? Okay, so the emergent just becomes difference, and we have a discretized charge density, and this is still, well, should still be a conserved quantity. Okay, so now the question is how to implement this. Well, the fermions we can still think probably we can do by just putting fermionic atoms in there. Okay, fine. But how do we do the gauge field? And so there are different ways. One way is this so-called quantum link model formalism, which Uwe and Zwiese introduced to the quantum simulation community. And then what one does essentially is one takes the electric field and cuts it off at some values minus s and plus s. So it's like truncating large field fluctuations. So this is done by replacing essentially these electric field and vector potential operators by spin operators. And so these ensure that, so we have this truncation here, but we also make sure that we have the good commutation relations. And well, so this, maybe at first you think, oh, this is a little bit weird, but it's actually nice. So this is still a gauge theory. It's still, for even small spins s, it retains interesting physics, as we're going to see. And if we take s large, then we recover QED in a very controlled way, as we can do by a finite s extrapolation and so on. So you can look at these works here, for example, to see that. Yeah, and so now the new theory that we want looks like this. Okay, so you have this fermions coupled to this effective spin degree of freedom, and then this discretized Gauss law. Okay, so let's see what do we need to do to implement that. Well, the difficulty is this process here. So that one is just some local interaction energy that's usually not so difficult. This one here is just a local chemical potential. It's even simpler. The difficult part is this coupling, and to do it in the right way. And well, so let's see what this does. Well, it takes two neighboring metasites. And for example, if they are initially in a vacuum state, this process generates an electron-positron pair, and then in addition screens the electric field accordingly to the new charge configuration. Okay, so this is what this process tells us. And the question is, how do we realize it? And so we have been working on that for many years. So actually, there's a long line of theory works from different groups which have proposed different lattice implementations, and then it becomes simpler and simpler and simpler. Every time there was one requirement that was found to be not necessary or could be replaced by a simpler implementation, until last year in the group of Freke and Gajewski in Heidelberg, they were able to implement a single building block in the limit of large S. And so the way that they did it is essentially to take one lattice, where indeed one would like to, so in the experiment they used also bosons, but conceptually you would like here to put the fermions that represent the matter fields, okay? And then on the links we put a very deep lattice that holds bosons, okay, in two internal states. And now the imbalance of these bosons tells us the spin, the tilt of the gauge link, so the level of the electric field. Okay, so we map this imbalance to the electric field, and then the basic process that we want is that one fermion goes from this side over here, and one boson goes from up here to down there. Then we have changed the electric field and we have moved a particle. So to implement this is by using spin changing collisions, which conserve angular momentum. So the lattice is actually shaped in a way that the fermion, once it tunnels, needs to change its internal state, and then it scatters with the bosons, which then also need to change the internal state to conserve total spin. Okay, and so then we have achieved that the particles can here and one can there. And then other things one can suppress by energy penalties. And well, actually, so we found even a simpler implementation which was done in the experiment, where this doesn't happen on two different lattice sites, but on a local one, and one uses an additional mapping and so on. So it becomes even much more simple and better scales and so on. Okay, so this is an implementation that works in the limit of large S, which is very nice. But at some point, we also thought, so can we not do it in the opposite direction of taking very small s and maybe try to find something simpler? So let's take even the extreme limit of s equal 1/2. Okay, so first of all, we don't need to care about this term anymore. It's just squares to 1, so let's remove it. And let's take another step. Okay, so we make a particle hole transformation on the fermions on every second side. So then we get the minus sign. So we remove the dagger here, and here we get an additional minus sign. Okay, so we get a slightly simpler Hamiltonian, which is more homogeneous. And now we can think about how we can implement that. Okay, so this is the basic process that we want. So instead of now having two different species, one can actually do everything with just a single bosonic species. So we can, for example, map this configuration to such a superlattice configuration. Okay, so now what has happened here? So we have alternating shallow and deep sides. And on the shallow sides, these we interpret as matter, as electrons and positrons, and the deep sides we interpret as electric fields. Okay, so instead of having bosons and fermions, which are gauge field and matter field, we now have just shallow and deep sides. This gives us the distinction. Okay, and everywhere in the shallow side where we have a particle, we interpret this as an electron or a positron. And then the basic process is we remove two atoms, okay, here, and then we put a doublon on the link. Okay, so that essentially the mapping is we map the fermions to hardcore bosons using the Jordan-Wigner transformation. And we map the spin 1/2, the link, which is now really just the spin 1/2, a very coarse-grained electric field. We map this to the occupations 0 and 2 of these bosons living on the link. Okay? And then the basic process just becomes remove these particles here and put 2 there. Okay? Okay, and then we go from here to there. So now the question is, how can we implement this? Well, it's actually quite simple, just in second order perturbation theory. Okay, so this particle, this atom can tunnel here. This side is very deep, so it costs lots of energy. It's only a virtually visited state. The second atom comes, and then by the interactions, they lift it in resonance. And so essentially the system moves between these two configurations back and forth. Okay, and then we realize this process here. And the rest mass is just the energy mismatch, a tiny little energy mismatch between these two configurations. So now what is nice about this implementation, it's a very simple lattice structure. It uses just a single atomic species, and it has very fast timescales because of the second order process. One disadvantage is it's very coarse. It has a very coarse-grained electric field, because it's just, the field can be just plus 1/2 or minus 1/2. Okay. So now one can wonder, does this actually still capture interesting physics? And yes, it does. So first of all, it's still a gauge theory, most importantly. And second, there's still interesting physics in there. For example, we still see a Coleman's phase transition. So the transition from matter, all these charges there fully overscreened, is this configuration is just all the shallow sides are full, particles everywhere. And then we go into the situation where all the shallow sides are empty, and we have generated doublons, and they can sit like this or like that, and these are the two configurations. Okay, and so now in the group of Zhanwei Pan and Zhenjiang Yuan in Heidelberg, where Bing Yang was the postdoc who did the implementation and most of the work. So they implemented this this setup, which they did in a very large system of 71 sites, and they could produce an almost perfect Mott insulator. So really, this initial state to a very, very good degree, and then just by tuning essentially the lattice depth here, the depth of these deep wells, they tune the rest mass and then can sweep through this phase transition. Okay, and so here, this is the result. They measured the matter density and also the electric field, and then see indeed how the particles go down in particle number. So we don't have anything on the shallow sides anymore. They've annihilated, and then we have doublons that come up, so the electric field has been generated, and indeed we generate large domains of the symmetry breaking. Yeah? And what's also nice, so we really had to push here the DMRG to do to compute this dynamics for this 71 sites. So we couldn't still compare it, but as I mentioned before, we are now close that it becomes actually difficult. Okay, so there's one last aspect that I want to mention. So it's really nice, yeah, they measured this phase transition and so on. But so no one can ask, well, such phase transitions, they appear in many contexts. So is this really a gauge theory? And for this, one thing that they did is they certified Gauss' law. So they measured all the configurations. As I said, there are only few configurations allowed, which map to these 3 configurations in the optical lattice. And for example, if we have 3 atoms on the deep side or 2 close to 1 or so, then these would be strange things like having a field line that enters, then a charge that sits there and the field line exits again in the same way. So this is something that Gauss' law doesn't allow. Okay, so we need to, only these 3 configurations are allowed. And well, they actually measured this in the experiment. So they combined different measurements. They don't have a quantum Gauss microscope, so they can't do snapshots, but they measured, they were able to measure different configurations and then sum them up the probabilities. And so they got an upper bound on the probability to violate the Gauss' law. And so this is the result here. And you see that it's a log scale as a function of the sweep. They stay on a very low level, smaller than 0.1. So there's at least 90% of the configurations fulfill Gauss' law. Yeah, so that's already a very nice result. And it's the first time that Gauss' law was certified in a quantum simulator, which I find very, very nice. But of course, one can play devil's advocate even more. So say, yes, okay, you certified the Gauss' law, nice, yeah. But you see, there is some violation probably. Yeah, it's an upper bound, but so we suppose we are close to the upper bound. So there's some violation. And if you violate Gauss' law, it's not fulfilled. So you don't have really a symmetry in the strict sense. And so what we did in the last year is really try to understand what these symmetry violations do. We did lots of simulations taking this quantum link model that we want, and then add additional terms, for example, in the numerics, this H1, which do not fulfill Gauss' law. So they should drive us out of the good configurations. But then we see also, if you put an energy penalty, which in the optical lattice is nothing else than these energy offsets that we put the chemical potential and so on, then we see if you do this, and if we look at the gauge violation, so how many configurations violate Gauss' law as a function of time, we can tune this in a very controlled way. So we stay for essentially infinite times. This is until 10 to the 10. We stay essentially on the level of having any desired level of gauge violation that we want by increasing these energy penalties. Okay, so making it harder energetically to leave to violate Gauss' law. And this also explains us why we stay on a low level here, because we have these suitably engineered energy penalties. Okay, but okay, so very quickly, so we can still think, so we can control it. Okay, that's nice. So we can increase the energy penalty, the violation goes down, but still, what does it mean? Huh? So we looked at local observables and see that they stay very close also during the dynamics to the ideal dynamics, but we can also look at this in the context of emergence of gauge theories in the ground state phase diagram. And now I think I need to conclude, so I just go quite quickly, because so we can study how this Coleman's phase transition is fulfilled if we add to the Hamiltonian a gauge violation plus an energy protection. Okay. And so we did this calculation. This was Martin van Dam who did this with IMPS in the thermodynamic limit. And so we can see that if we have these bad terms that break Gauss' law, yes, the violation goes up, but we can also see that this phase transition persists up to a certain value. So we see the same physics until the gauge violation becomes on the order of 1 of the energy scale of the good model. Huh? So we can do very, very large gauge breakings and still see the same physics. And if we look at the fidelity susceptibility, we see here is clearly a phase transition. So down here, we have actually a renormalized gauge theory, and up here we could interpret this as a Higgs phase. Okay, and so
sorry to interrupt, Philip. We need to wrap it up in a couple of minutes if you can.
I'm concluding. Yeah,
yeah.
Exactly. So
thanks.
Okay, so exactly. So yeah. So we see we get so it's safe. We get a renormalized gauge theory in a very large region. Okay, good. So and we can look at the renormalization of that and so on. So what I showed you here is, So now we have really large-scale implementations available where we can look at many-body physics. There are lots of interesting phenomena, many-body phenomena to look at there, which have been discovered in the last years. So there's lots of physics, even in the simpler models. And we have studied a lot the reliability to really see if we scale them up, how well will this work. And now we need to do the next step and make things more complex. And so, yeah, so there's lots of things still to be done until we really can do high energy physics that is relevant for experiments, but we can also already look at interesting phenomena right now. And here, there's lots of reviews that I invited to look at. And the most important slide, I want to thank to my group members and all the collaborators in this really community effort. And also thanks to you.
All right. Well, thank you very much, Philipp, for the very enthusiastic talk. So I think we ought to, at this point, skip the Q&A and then push the questions into the roundtable at the end of the session. In which case, we'll just move on to the second speaker of the day.